Hey everybody, and welcome back to Algebra 2 Online. So the plan for today is to talk about what I got right up here, the number and nature of roots for these higher order polynomials. So there's a lot of patterns that I basically want you to see, and one of them has to do with just the degree alone, and then another pattern has to do with the degree and the sign of the polynomial. So whether the leading coefficient on the thing is positive or negative. So one of the things we kind of honestly already talked about, and that's like this one up here. So we talked about that fundamental theorem of algebra a little bit last time, and we said that the number of roots should always match the highest exponent. So if you've got a linear polynomial, you should only be expecting one root in total. And if you've got a quadratic, right, you should be expecting 2. And if you've got a cubic, you would be expecting 3. And like it just keeps going, right? If you've got an x to the 4th, which is a quartic, you would expect 4. The thing that we didn't really talk about is down here. So if you take this degree into effect, but this time also take into effect the sign of the polynomial, you will notice something kind of interesting that happens. And I just realized my color coding is off, and that's going to bug me. So I'm going to fix it. It's not perfect, but there you go. So if you, and for these ones, you might want to think about like a picture. So if you think of like y equals x, like this, right? As x goes out to infinity, right? You should notice that the function value is also going out to infinity. And as x goes out to negative infinity, right, then the function value will also go to negative infinity. Basically goes in the same direction. And then if you take a quadratic, just like x squared, like that, as x goes out to, we'll start with infinity again, then the function value goes to infinity. And as x goes to negative infinity, the function value also goes to infinity, right? They both end like up in the same direction like that. And then x cubed, so a normal x cubed looks like that, okay? But we have a negative one, so we would flip that thing around, right? And we saw these back when we did that like function transformations project a while back, but for like a negative x cubed like this one, as x goes to infinity, right, you'll notice that f of x goes down to negative infinity, and as x goes to negative infinity, f of x goes to positive infinity. And this should kind of be enough to start seeing the pattern that I want you to see, and we could keep doing it, but if this is basically what I want you to see. So if you have an even degree polynomial, they're always going to just end in the same direction. So here, for a positive one, they always are going to end up. If it's negative, they always end down, okay? And then if it's odd degree, basically they're going to always end in alternate directions like this, like, either pointing up at the right and down on the left, or up on the left, down at the right. If I had gone one more, if you, there's x to the 4th graphs that look like stuff like that, okay? Basically, the way you want to look at this is, it's honestly like you have an x squared, and then you have just like another x squared. And so you get a, it's kind of like x squared plus x squared. You add the exponents and you get an x to the 4th. This one being this would be a positive x to the 4th. It would end in the same direction. If I went one more, if I did x to the 5th, all right, maybe I'll do a positive x to the 5th. It would look like 1, 2, so that's kind of x to the 4th right now, and then I'm just going to shoot off in a different direction. So this one, right, you can think of it as, here's like an x squared, and then you can think of another x squared, and then, it's kind of hard to show, but it's like a half of an x squared. That's how you want to look at these things. And and that would be a positive x to the fifth right here. But this is definitely something very important to know. So even degree polynomials end in the same direction, odd end in opposites, okay? And you always are going to match the degrees with the number of roots to see, okay? All right, so just kind of looking at some pictures of what these weird graphs look like. Basically, there could be multiple answers for these, but what I'm going to write down is the minimum number of real or imaginary roots for each, and whether or not it's even or odd, okay? So even or odd, you can just do based on really this part. Even, end in the same direction, odd, end in opposite. So, this first one up here, ending in opposite directions, so it's got to be odd. This one down here, it's ending in the same direction, so it's got to be even. And then the last one here, ending in the same direction, so it's got to be even again. And in terms of roots, okay, a real root is always just going to be like this green dot right here that I now just made red. It's always going to be like a spot where it crosses the x-axis. And then, you can think of like this right here. This is like a quadratic that's part of this thing. And that quadratic in there will have like two imaginary roots, the way that they've had two imaginary roots before. And then likewise, like this part can be thought of as another quadratic that has two imaginary roots. And then you have this weird like half over here. And so this is an example that would be odd, and the minimum number of real or imaginary, it would have one real, and it would have four imaginary. You want to look at this as sort of two quadratics, giving you four imaginary roots, and then one real root like that. It's kind of like if you combined a line with a quadratic and with another one, right? It's x plus x squared, you kind of get up to x to the fifth. This one down here, so if you look at what we got, you got 1, 2, 3, 4, 5, 6 real roots, and that could just be it. You could just basically have this be an even polynomial with 6 real roots, and that would be like the minimum number. You want to think of this one as like a quadratic there, another quadratic there, and then a third quadratic there. Basically, it's, just 3 x squared stuck together in a sense, and you're going to get 2, 4, 6 real roots. This one down here, it's going to be even because it's shooting off in the two same directions, and basically has no, there's no spot where it crosses here, so it's got no real roots, and then, no real roots. And then it has to, it's minimum, because it's got like these two bumps. Basically, it's having something like 2 quadratics. So as a minimum, it could have 4 imaginary roots. And so that's like just an important part of the pattern associated with the graph of these things. All right, so kind of opposite question now. So I want to graph some polynomials that do certain things here. So if I wanted an odd function with zeros at -5, -3, 0, 2, and 4, that could be like all the roots I have, right? If it's odd, you could just say it has 5 roots, and that's an odd amount, right? So you have a root at -5, -3, 0, 2, and 4. So you could just do something like boom, 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 boom. And that really does it, right? It goes through all the roots I needed. This could basically be some sort of positive x to the fifth graph. It is not what x to the fifth exactly looks like, because we'll talk about that more as we go on. But if you plug in x to the fifth to like Desmos or something, you're definitely not going to get this. This would just be an example of what an x to the fifth could look like. All right, so this next one, I want a 4th degree function with a 0 at -3, max at 2, and a repeated or doubled root at x equals 1. Okay, a lot more going on here. So let's just start with, I think I'll be able to fit it right there. So fourth degree, right, means it's just shooting off in the same direction. And, we need to have 4 roots, okay? It definitely has a 0 at -3. So 1, 2, 3, we have a root, okay? It also said there's a max at 2. So if I go 1, 2, I know that it's never getting higher than that, basically, okay? I'm going to erase that for a second, but, okay. So that 2 is going to be the highest I ever go, and it has a repeated or doubled root at -1. Actually, I think I'm going to make this a bit bigger. I'll space this out a little more. Okay, there we go. So if you remember back to quadratics, you're going to hear me say that a lot. When we had repeated roots with quadratics, right, those were things like, you could have just something like this. That graph could be, x minus 2 quantity squared. This would just be over 2. But the repeated roots were the ones where basically the graph came in and just like touched the x-axis and then bounced back up. And so we need to do that over here for my repeated root at -1. And then we've got to make sure that we go through this 0 here as well. And we got to keep in mind that we never go over 2. So if you go through all of that, basically you've got, you can have this as a graph. So bounce right there. So that's going to be a repeated root. Maybe it comes up and actually hits a max of 2 right there. And then you could come back down like that. So this thing has 1 root here, repeated root here, that's 3. We know there's got to be another root. So another one right here. And we never went higher than 2. All right. And then last but not least, I want a sketch here of a 6-degree function that has a max at 3 and 6 unreal roots, okay? And a lot of times when people read this one, it sounds a little confusing because if you have a max of 3, a lot of students want to do something like this. They want to make some sort of graph, and then like at 3, they want a max, but this thing, if, a lot of maximum kind of problems do stuff like I did over here, that they're going to then, decrease down in both directions like that, which would then give you real roots, right? Because you're crossing the x-axis somewhere. So you need to do something else. Honestly, what I did is pretty much right. You just need to do it not crossing the x-axis. So you could absolutely have a 3 there, and then you could just do like, here's 1 quadratic, 2 quadratic with real roots, and then max, we're just going to stay just shy of the x-axis to make sure it's a real or unreal root. But basically here we got like a quadratic with 2 imaginary roots, 2 more imaginary roots, and then here's my maximum at 3. And this is definitely 6 degree because 1, 2, 3, 4, 5, 6. All right. So this last thing, I just want to kind of introduce how we might go about and do some sort of application-y kind of problems with these. So this one says, annual admissions to movies in the United States can be modeled by this function. Back in the day when we used to go to movies. X is the number of years since 1926, and f of x is the annual admissions in millions. And I found this somewhere, and I have no idea of how accurate it really is, but supposedly it is. And so a lot of problems in the real world are going to have crazy numbers like this. And this one right here is a good example of one that I could use to motivate what's kind of down here. So one of the things that I'm going to want you to know how to do is to use a few buttons on your calculator, specifically actually something called the max, min, and zero buttons. And I'm not going to be able to do it in this video because I can't record my calculator here, but I wanted to just show the problem, and basically in another video I'm going to show you how I can use my graphing calculator to analyze different things like this about it. So I'm going to talk about how to find the value of all the turning points of the function, and then using that I can, in my calculator, I can kind of sketch it, also using a little bit more features from my calculator, specifically again this thing called the max, the min, and really that's, I guess, even up here, the max, the min, and the zero buttons. And then once we have a picture of it, we can talk about this. So we can talk about, do these kind of trends, do you think they're going to continue, basically? A lot of models, you'll notice, work for certain kind of x values or something, but then their usefulness sort of tapers off because of different reasons. And you'll see when we do it out. Actually, I'm going to talk about that one really quick right now, because so right now, if you look at it, right, we have a negative x to the fourth. And so without even really graphing it formally, which I will do in another video, we could imagine x to the fourth could look something like that. And this says, would this trend in movie admissions, what does it basically suggest? And then, is it reasonable that the trend will, it's supposed to say, continue, weird, indefinitely. And, if you think about it, a negative x to the fourth, continuing indefinitely means you're going to go into the negatives, right? And f of x is the annual, admissions in millions, and you can't have negative admissions. So, to answer this question, basically, no, it's not reasonable to think that trend will continue. And, the trend is basically that it's going to decrease as time goes on. So what a model like this in the world can mean is that it could be really useful for, from 1926 or something, on for a certain amount of time, but then eventually that model just isn't good and we need a better model. So I will do a screencast and I will show how I can go about doing this on my calculator for you in another video.